Hello, everyone. This is Manuel and Maria, and we are presenting our final project on discrete event simulation applied to sugarcane harvesting. So I'm going to explain the process we considered. So sugarcane is harvested by a harvester that drops the crop into a wagon, and the wagon delivers the crop to the edge of the field where it is stored until trucks come to pick it up to deliver to a biorefinery where the sugar content is extracted to produce biofuels. So plants have a peak sugar production, and we want to know, we want to find when to harvest each plot to maximize the sugar production. We also want to know the number of harvesters and wagons that we need, the size of the storage area, and the number of trucks, the optimal numbers. And we want to determine optimal policies for when to harvest and how much equipment we need. So our objectives are to maximize the sugar mass delivered to the biorefinery and minimize the storage needed. We made different assumptions, taking information from literature and the US Department of Agriculture. For example, for the crop yield and sugar concentration time series, we assume them to be normally distributed with a stationary correlation function. So variables are both spatially and temporarily correlated. And well, sugars also decay after harvesting, following an exponential first order decay model. We defined the moment of harvest when a target concentration is reached of sugar, for example, 13%, or a limit of late harvest of 180 days. And we use an average size farm for Florida and divided it into 25 plots. And we assume different values for service rates of our equipment and other parameters. Well, for the model, we are not going to list all the attributes of our entities, but mainly we have the crop as a transient entity, and we're using 1 unit of crop equal to the wagon capacity. And our permanent entities are harvesters, wagons, trucks, and the storage area. We used extreme values for verification, to check, for example, when we have infinite number of our resource, all the end of services occur at the same time for any batch arrival. So we can see no slope on the lines in the plot. And when we have only one of an equipment, each end of service happens one service time before the previous one, represented by the slope of the lines in the plot. Since we don't have any farm information to validate, we checked that our end results made sense in terms of how we expect the system to behave. So we're working with a multiple server queue with non-empty initial conditions and batch arrivals. And the workday was assumed to be 12 hours per day, canceling only the beginnings of service and not the arrivals of the crops, since crops can mature during the night. And then crops arrive when we assume they matured in batches equal to the randomly generated mass of each plot. The harvesters and wagons work together in the begin harvest, and after a service time, the harvesters become available, but the wagons have to deliver the crop to the storage area and then come back to the harvesting site. And from the storage area, once the truck capacity is reached, trucks deliver the crop to the biorefinery and come back to pick up more. And this is a complete model, but for simplicity of coding, we decoupled it into 2 models. So in the first model, we saved the times the crop arrived to the storage area, and we used that information to drive the arrivals in the second model, but functionally they are the same.
In terms of our result, we consider different cases. We consider for them 3 different values for the number of harvesters, 3 values for the number of wagons, 7 values for the number of trucks, and 4 different target sugar concentrations that correspond to each of the plots. These plots show the results of 100 different runs. Lines represent point estimates of expected total sugar mass, so the full lines or the dashed lines. But the shaded region show the 95% confidence intervals of them. Optimal policy appears to be dominated by the decay of sugar after harvest, which is much larger than the decay in the plant. Therefore, having enough trucks to remove storage, which is the cases on the right of the plots, to remove storage as soon as possible has great positive impacts on yield. However, increasing the number of harvesters hurts yields. So increasing the number of harvesters going out here hurts yields since it increases the rate of arrivals at storage, increasing time for decay to occur. We recommend using a target concentration close to the mean maximum, using few harvesters, and using enough trucks to have minimum storage. Here we show point estimates and confidence interval for the expected value of the maximum needed storage for the same cases considered before. As noted before, the cases that show the highest yields correspond to the minimum storage. So this means that our 2 objectives align and the previously stated recommendations are valid. We use since our variabilities are large, we use the method of control variates to reduce variance in our results. As a control variate, we use the total stock mass yield in the farm. Since this is a randomly generated value coming from a multivariate normal distribution, the expected value is known to be the sum of its means of the means of each distribution. We use this control variate since the sugar mass yield is strongly positively correlated to the total mass yield. For each case, we found the value of the parameter alpha that minimizes the variance, and we use these values for the computation of the variance reduction. The variance reduction is such that our confidence interval shrinks by 70%. This improvement would require around 10 times as many runs if no variance reduction was used. Similarly, we apply the same method for the expected maximum storage. We use the same control variate since we expect the total mass stored to be positively correlated to the total mass yield. We obtain similar reductions in variances. Finally, here we show our results for 2 possible optimal policy solutions. In both cases, the optimal target concentration is 14%. The one that uses the most resources, the one at the bottom, doesn't have statistically significantly superior yields. So if we needed to distinguish between them, we would have to obtain tighter confidence intervals. Both model simplifications and errors in the data can be sources of errors for our outputs. However, since our policy recommendations are dominated by the sugar yields and decay, we consider those to be the most important to be determined. So this is our presentation. Thank you very much. Bye.
Thank you.